Hey everyone, how goes it? And welcome back to Computer Science 146. Today, we're going to introduce another new data structure called stacks. Now, stacks are a very similar data structure to a queue. In a lot of cases, they're considered to be sibling data structures because they are very similar. They basically process information based on time. However, the large difference between a queue and a stack is a stack reverses the order. A queue is first in, first out, FIFO. A stack is last in, first out, LIFO. Stacks are great for processing data in reversed order. They're also a great data structure to use this technique called backtracking. Now, just like before, with a queue, a stack is essential to how we do computing. Now, when we were thinking about queues before, we were considering the processor running commands first in, first out, one at a time. Now, also, we understand that inside of memory, there is this special section called the call stack. This is how methods and functions work inside of our code. As we know, the entry point of our programs is the main method. This method is loaded and pushed onto the call stack. Now, every time we've called a method, it has been loaded and pushed on top of those methods. This allows us to effectively follow that code to a different part, to a different method, run that code, and then once that method has been completed, it allows it to return back from where it was called from. What I've just described is an example of backtracking, following from one part of code to a different part of code, and then returning back to that same part of code. Now, understanding that, we have to review some of the stack operations. Whenever you're adding something to a stack, it's called pushing to the stack, and you always push to the top of the stack. Whenever you're removing an element from a stack, it's called popping, and you always pop off the top part of the stack. Now, the other two methods are just the same as with the queue, peek and print. Peek allows us to observe the first element of the stack without removing it, and print prints everything out in stack order. Do keep in mind that stacks reverse the order in which they arrived, so stacks reverse that order. Now, just like with the queue, we can implement a stack using those foundational data structures like an array or like a linked list. The big difference now is there's only one major reference, the head, whether it be the head index for an array or the head reference inside of a linked list. We don't require a tail this time because keep this in mind. When we were adding to the end of a queue, we had to add it past that tail reference. However, with a stack, we add and remove at the head. Now, much like before, stacks can be implemented as an array or a linked list. In order to do this best in coding, we recognize one thing can be implemented in multiple different ways. In order to best do this, we're going to create an interface which defines the methods that we have to have in every implementation of our stack. And as we can see here, the methods that we have for the stack interface are push, pop, peek, and print. Let's now go over to the code and start implementing some stacks. As you can see, we have our project set up and ready to go. The first thing that we're going to do is create the stack interface. What I'm going to do is create a new interface, and I'm going to call it stack I. Now, this stack should be generic. It could be a stack of any type. To make sure that's true, we use the angle brackets in that type T, and now this is a stack interface of whatever type. Interfaces do not contain any functional code. They just contain method definitions, and these methods must be implemented in any class that uses this interface. So the first one, public void push T a data. We're adding something to the stack. Next, public T pop. we remove the first element from the stack. Public T peek. We observe the first element, but don't remove it. And finally, public void print. Just print everything out in stack order. So now that we have this, let's see what we can do with it. I'm going to go ahead and I'm going to create a tester once again to show off some of the functionality that we're developing along with this stack. Now inside of here, we're going to declare a new instance of a stack. So I'm going to call it the stack I, and I'll just call it stack. And what kind of stack are we going to create? Well, let's keep it very simple and create a stack of integers. This is all we can do so far because interfaces cannot be constructed. So now we have to create a class that implements that interface in order to use this. The reason why we like using this is because the interface becomes a type, and that type can be used as basically a variable for however we're setting up the back end. So in other words, is this an array stack or is this a linked list stack? If we have both of them implement the stack interface, it doesn't matter. We can change this by just changing how it's constructed. Now let's start developing an array-based stack. We're going to go ahead and create a new class, and we're going to call this the array stack. Now this array stack is also generic. It could be of any type. And also, we make sure that this implements the stack interface, also of type T. Now, anytime we use the type stack I, we can substitute an array stack for it. Now we need to write some properties. Private T array, and this is going to be the array stack. From there, we're going to go ahead and create a private int head, which is going to be our head index. And always keep in mind, this is the first null element. Now the last property we're going to create is a constant that corresponds to the default size of this stack. Public static final int default size, and we'll just set it to something arbitrary like 100. Now let's create some constructors. Public array stack. Now this is our default constructor. Now we're going to create one parameterized constructor, and the only parameter we're going to use is the size. Now as both of these constructors are initializing all of these different values, we're just going to create a different method, public void init, also with the size, that's going to initialize these properties. So in other words, this method is simply just going to be called by this and this. Now we have to check whether or not the size is correct. And I'm going to argue that an array needs to be at least size 1. So if size is greater than or equal to 1, then we consider the parameter size to be correct. And if that's the case, what we need to do is assign the stack to typecast TArray, and then we construct a new object array of this size. We cannot construct the type T. However, we do understand that every type T inherits from the type object. So by doing this, we do construct this object array and then cast everything as this specific type. Now, if that's not true, we still need to construct our stack. So what we're going to do is typecast this T array, but this time, this new object array is going to be of our default size. And finally, to finish this, we're going to call init from both of our constructors. The default constructor is going to call init with the default size. And our parameterized constructor is going to call init with this size. Now, one last thing. We're going to assume that the head index starts at index 0. The head is always going to refer to the first null element. If the stack is empty, that means that the head is referencing index 0. Now that we have all of that, we need to start developing that other functionality, push, pop, peek, and print. Let's take a look at how push works in an array-based stack. Now this is the way that we can start thinking of this array-based stack. If basically we're assuming that we start at index 0 and this head index always refers to the first null element, what we do is basically as we're adding elements, we advance the head pointer forward or the head index forward, and as we remove, we just move it backwards. So basically a stack just grows from index 0 forward and shrinks backwards. We do not have to worry about circular references for this because of this structure. So now, understanding this, when we need to push or add a new element to the stack, what we do is we add that element to where head index is referring to and then increase the head index by 1. So if we're going to add the element 4 to this, then we just add it to that location and then move the head index forward, and now it's referring to 5. One detail to keep in mind, the top of the stack is at the head index minus 1. This is very similar to how tail was used in a queue. Let's go ahead and implement push. Back inside our code. Public void push TA data. One thing that we have to keep in mind is an array is not resizable in memory, so we could run out of room in our stack. The way that we could tell is by using the head index. So if head is equal to, actually, let's go ahead and make it greater than or equal to stack.length. That means this head, which corresponds to the first null index, is outside of the valid indices for this stack. If that's true, we can't add anything to it, so just return. However, if that's not the case, then we just take stack at the head index and have it point to a data. And then head plus plus. And so that is push for an array-based implementation of a stack. Now let's start removing elements. Let's see what pop does. So the idea of pop is we have to remove that top element, or in this case, the element that is at head index minus 1. The first thing that we do is we save a reference to that stored data. So if we take this head index, which is currently at index 4, 4 minus 1 is 3, we save the data that's stored at index 3, which is 6. What we then do is move back the head index by 1. And that's it. Now you may have noticed that we didn't actually remove this information from here, and we don't really have to. Keep in mind, when we push, when we add information to the stack, we simply write that information to where the head index is referring to. So, in fact, the next time we push, this is just going to be replaced with the new element. Now, let's see how pop looks inside a code. Going back to here, we're going to create public T pop. Now the thing is, we might have an empty stack, and the way we can tell is if the head index is equal to 0. As the head index refers to the first null element, if the 0 index is null, that means nothing is in here. If that's the case, just return null. But otherwise, we're going to set tret is equal to stack at this head minus 1. Then head minus minus and return ret. And that's how you remove or you pop off an element from this array-based stack. Now let's finish this off by writing peek and print. Public t peek. This observes the first element without removing it. However, once again, if head is equal to 0, then we need to return null. There's nothing there. But if that's not the case, return stack at head minus 1. Finally, print. Public void print. Now this is where we have to recognize that this has to go in stack order. Now it's easy to mix this up because you may think starting from index 0, that is the stack order going from 0 to the end of the stack. But that's not the case. The head is at the beginning of the stack. So we need to start this for int I is equal to head. Now the head itself refers to the first null index, so we have to subtract 1 from it. Now we start I at the head index. Now while I is greater than or equal to 0, I minus minus. Remember, stacks are last in, first out. They go in reverse. Inside of this for loop, I'm just going to call system.out.println stack at index I. Now we have successfully implemented an array-based stack. Let's now apply that in our tester. Going back to here, now that we have declared there's going to be an instance of a stack, we need to construct it. So we're going to set stack is equal to new array stack of type integer, and we're just going to call the default constructor. So now we've constructed an array-based implementation of a stack. From here, let's add elements. So for int I is equal to 0, I is less than, let's say 10, I++. Inside of here, stack.push, I. Outside of the for loop, stack.print. Now, let's see what prints out. And it looks like everything printed out successfully. Now keep this in mind. The for loop goes from 0 to 9 in that order. This is the stack order, which is last in, first out. The first element pushed onto the stack was 0, then 1, then 2, then 3, then 4, then 5, 6, 7, 8, and 9. However, the stack reverses that order. The first element in the stack is 9, which was the last element that was added to it. Let's pop off 2 elements, stack.pop and also int val2 stack.pop, stack.print. Now let's see what happens here. Now the stack starts right there, and as you can tell, we've popped off the values 9 and 8, and now 7 is at the top of this stack. This is a last in, first out data structure that is now implemented using an array. Let's now implement this using a linked list. Now we're going to start this off just like we have created the generic linked list and also very similarly to how we created the queue. It turns out when you're making a linked-based structure, the first parts are very similar. So let's go ahead and start by creating a new class. and we'll call this the LL stack, linked list stack. This linked list stack is a generic type which also implements our stack interface of type T. Now, as this is a linking structure, what we do is we create a smaller structure internally to keep track of these nodes. Nodes are a structure that groups together the data with a link, and we're also going to use a singly linked list in order to implement this stack. So first thing, we create a private class list node. This list node is going to group together the TA data and also the list node link. Then we create a parameterized constructor, public list node, and we pass in T, A data. And you know what? To make this consistent, instead of calling this A data, I'm going to call this data instead. And also the list node A link. Then we assign data to A data and this link to point to A link. Now we have this structure that's going to be used for our nodes. What we need to do then is create a very specific type of reference inside of the stack, which is always referring to the first element. Once again, we're going to create a private list node head, which always points to the first element in our stack. After that, we're going to write the constructor. Public LL stack. And simple enough, we're going to point head to null. Head is the only reference we need for a stack because all of the operations push and pop only deal with the head. So now that we have this, let's explore how we push using a linked list stack. Now, when we're going to push, or in other words, add something to a linked list stack, well, what we have to do is what we've done before when we're adding a new element to this linked structure. We have to create a new instance of that list node with the data. Once we've created a new instance of that list node, what we then do is we have the link to that newly created list node point to the head. Then we update the head reference to refer to that newly added node. So, for example, let's say we're going to add the information 4 to this linked list stack. Now, as you can see, the node that contains 4 has been created. What we then do is take its link and point it to where the head is pointing to, just like this. Then we update the head to point to that newly created node, so now this becomes the head. This is basically enqueue, but in reverse. Instead of adding to the tail, you're adding to the head. Now let's see how that looks in code. Coming back here, what we need to do first is public void push TA data. After that, we construct a new list node, new node, and set that equal to new list node. Now this constructs our new node. What we need to do next is pass this data to get stored into this new node, A data. Now what we need to do is set the link. Now before, we've been setting the link to null because this has been at the end of these different lists. But what we're doing here is adding it to the beginning. So what we want to do is have this new node refer to the head. After that, we reassign the head to point to the new node. In other words, the head is going to store the memory reference that is stored right here, and now this new node becomes the head. And that's it. That's all you have to do to push a new element onto a linked list stack. Now you also may be wondering, why didn't we put if head is equal to null and deal with that case? And simply enough, we don't have to. By doing it in this way, no matter what, if the head is null, it's going to be assigned to the value of this new node. So we don't even have to worry about that case. The next thing that we do have to worry about is how do we remove an element off of this stack? Let's see what that looks like. Now, when we are popping or removing element from a stack, what we do first is something very similar. We have to save a reference to the data that's stored in the head. Next, what we do is we move the head reference forward and then return that data. So if we have this kind of structure, the data that's stored in the head is 6. So we need to store a reference to that value. After that, we move the head forward. And knowing that Java is a memory-managed language, which means it has a mechanism called a garbage collector that goes around and basically finds unreachable parts of memory, like this part right here is no longer reachable, we know this element is then simply deleted. Let's see how that looks in code. Down here, public t pop, removing something. Now in this case, we do need to check if head is equal to null, then return null. We do this because we have to save a reference to the data at the head. So t-ret is equal to head.data. The thing is, I'm calling a property from this object. If head was null, then we would get a null reference exception right here because we're trying to access data in an object that doesn't exist. So in this case, we have to check whether or not the head is null. Now that we have that, all we have to do is assign head to head.link, thus moving the head reference forward, and then return ret. And that's pop for a linked list stack. Let's go ahead and write the other methods, peek and print. Public t peek. This observes but doesn't remove the first element. So, if head is equal to null, we'll return null. Otherwise, return head.data. And finally, print. Public void print. We're going to do for list node temp points to the head, while temp is not equal to null, temp equals temp.link. Side here, system.out.println, temp.data. And now we've implemented everything in this linked list version of a stack. Let's test it out and see if it works. Going back to the tester, I'm now going to change this implementation here. We have this stack interface, which means I can construct an object that implements that interface. Now the array stack was the first one that we wrote, but then we wrote a different version called a linked list stack. By changing this one statement right here, I've effectively changed the entire back end of this software. No longer are we using an array-based implementation, we're using a linked implementation to do all of these actions. Let's see if anything changes. And as we scroll through this, 9 through 0, then we pop off 2 elements, and then 7 through 0. Effectively, nothing has changed except for the entire back end of this software. By creating this as an interface, we now have the flexibility to use an array or a linked list however we see fit. Both stacks and queues are integral to computing. Queues are first in, first out data structures. They process information one at a time in order. Stacks are last in, first out, and so they process information in reverse order. We're going to start exploring some more advanced data structures past this. Until then, I'll see you next time.